first part of the learning objective, which we are trying to define electrolysis, electrolyte, electrode, anode, and cathode. So we are going to the next part of the learning objective where we are going to explain the basic principle of electrolysis. I think we did this as well. So we've achieved the first two objectives. So let's go to the Faraday laws of electrolysis. Here we'll look at the first law, and then later we'll look at the second law. I believe we will cover both laws in this video. So let's start with the first law. The first law is just about the quantity of the electricity that is produced at each of the electrodes. So the first law states that the mass of a substance deposited or liberated at any electrode is directly proportional to the quantity of electricity passes through the electrolyte. So in a simpler term, the more electricity that you push through the electrolyte or through the circuit, the more stuff you get at the electrodes. So it makes sense because the more power means more work done in terms of a chemical change. So let's represent this mathematically, and then we'll use this to do the calculation involving the first law of electrolysis. So mathematically, the law can be represented by what we have here. Mass is directly proportional to quantity of electricity. M stands for the mass of substance deposited or liberated in grams. So it is mass in grams. And then the Q here represents the quantity of electricity passed through the electrolyte or passed through the system. And this is measured in column. So it is measured in columns. So this is the meaning or what the mass and Q represents. So remember from your physics experience that Q equals I times T. That is, I is the current and T is the time in seconds. So this current is measured in ampere, and then time is measured in seconds. So it means we can substitute for Q in the above equation. So we can have M is directly proportional to I times T. So again, this is still a proportion. It is not an equation yet. So how do we turn this to an equation? So if we turn it to an equation, we'll be able to use it to do our calculation. So to turn this to an equation, we need a constant. So we have to convert the proportionality over there into an equation using a constant. So this constant involves the Faraday constant. We call it Faraday constants and the molar mass. So it involves the Faraday constant, which is F, and then the molar mass of the substance that is produced. So we need some number. It's also the number of moles of the electron that is produced at the same time. So we need three quantities now. The first one is the Faraday. So talking about the constants, so we need to convert this one to an equation. We need Faraday, we need the molar mass of the substance, and then we need number of mole of electrons that is required for the reaction. So 1 Faraday, 1 F, is the quantity of electricity carried by 1 mole of electrons. So you need to understand that, or you need to know that. That is 1 Faraday, 1 F is the quantity of electricity carried by 1 mole of electron. So it means 1 Faraday equals 96, if you remember, 96485 coulomb. So that is 1 Faraday coulomb per mole rather of electrons. So I can say coulomb per mole of electrons. So sometimes you will see it, they will write it as, remember in your physics, it will be written as 96500 coulomb. So they usually write it that way, which is okay. So let's now change this. Let's change this this proportionality. Let's change it to an equation. We know all the quantity that we need in that equation. We need Faraday. We need we need the molar mass of the substance, and then the number of mole of the electron. So it means m now, instead of this, so we change this one to equality mass times the quantity of electricity divided by the number of moles times the Faraday constant. So remember, I want you to see very well that this is capital letter M and this is a small letter m. Small letter m represents the mass of the substance, and the capital letter M, represents the molar mass of the substance. So where Q is the quantity of electricity that is measured in coulomb, and then N is the number of mole of electrons involved in the half reaction, that is number of electrons that involved in the reaction at the electrode we are talking about, because reaction at each electrode is a half reaction. We'll talk about that as we go. And then F represents the Faraday constant, which is 96500 coulomb. So based on that, we can do some calculation. But before we do some calculation, let's look at this example first. So I have this equation. So this equation represents the deposition of copper at the electrode. If you look at this, you will see we have copper ion plus 2 electrons. So that is gaining of electron. So that should be reduction. So copper ion gains 2 electrons to become copper solid. Remember we said oxidation is loss of electron and reduction is gain of electron. And you can see this plus, this one means plus electrons. So it means copper ions gains 2 electrons to form copper solid. Now, in this equation now, we can get some values here. If you look at here, we said 2 moles of electrons. So 2E minus means 2 moles of electron. If you remember N, our N here represent what? It represents number of moles of electrons. So in this equation, N equals 2. I hope you get that. So let's look at the following example. So the equation says a current of 0.5 ampere is passed through a solution of silver nitrate for 30 seconds. Calculate the mass of silver deposited at the cathode. Ag, that is the molar mass of silver, equals 107.87 grams per mole. So let's look at the steps that involves in solving this problem. So the first is to write a half equation for the reaction, that is for the deposition of silver. It is very important. That is the reaction that happens at the cathode. Remember, silver is deposited at the cathode. And remember we said at the cathode, reduction occurs. So it means even if you don't know anything about that equation, we know that it's going to be plus electrons, something plus electron, to give us the silver that is deposited, which is Ag. So that is silver that is deposited at the cathode. So what should this one be now? This one would be silver ion. because it is the ion in solution that accepts electron to give us the metal at the cathode. And the metal that is formed at the cathode is silver. So it means silver ions in the solution gains electron. Now, the next thing which you are supposed to know actually is the charge on silver ion. It's going to be Ag plus or Ag2 plus. So you need to know this. Silver will lose only one electron. So the charge on silver ion is just a plus, just positive charge, not 2 plus. Can only lose one electron. So the silver ion will be Ag plus. So Ag plus gains one electron to give us Ag solid. Ag plus is aqueous because that is ion in the solution. So we have that. From here, we know the number of mole of electrons that involve in this deposition. That is, 1 mole of electron is needed to deposit 1 mole of silver solid. Now, that is the first part. The second part is to calculate the quantity of electricity. So remember, we know that Q equals I times T. And in the question, we're told that the current is 0.5 ampere and time is 30 minutes. So it means we can plug in both of them over there. So I is, let me write it, I equals 0.5 ampere, while time is 30 minutes. But if you remember, we said time has to be in what? It has to be in seconds, not in minutes. So we need to convert 30 minutes to something in seconds. How do we do that? We multiply by 60. So 30 minutes times 60 will give us 1,800 seconds. So this is what we need for the calculation. So Q now, we can calculate our Q. It's going to be 0.5 times 1800, which will be, that is 0.5 ampere and 1800 seconds. And then eventually, our final answer is going to be 900. 900 watts. Remember, the unit of quantity of electricity is coulomb. So 900 C. 900 coulomb of electricity. So that is the quantity of electricity for now. But if you look at the question, calculate the mass of silver deposited. So in order to calculate the mass of silver deposited, we need to know the quantity of electricity that deposit that silver. Now, we can go ahead and apply this formula. Mass of substance deposited will equal to the molar mass of that substance multiplied by the quantity of electricity divided by the Faraday times number of mole of electrons. So, and then what is the molar mass of silver? Remember, it is 107.87. That is grams per mole. Then multiply by what we just calculated now, which is 900 coulomb of electricity divided by what is the Faraday? Faraday is 96500. I will use 96485. 96485 coulomb per mole, then times the number of mole, which is only 1 mole. Remember, N is 1 mole over there. So if you press your calculator, you will get 1.006 grams of silver deposited at the cathode. So that is how to apply this formula, that is, apply this equation to calculate the number of the mass of substance that is deposited either at the anode or at the cathode. So in this example, it is the mass deposited at the cathode. So remember, in order to summarize everything, we talk about the Faraday's laws of the first law of electricity, and then we did some calculation regarding the first law of electricity. So we said that uh, the Faraday laws, the Faraday first law of electricity says that electrolysis says that the mass of a substance deposited or liberated at any electrode is directly proportional to the quantity of electricity passed through the electrolyte. And then we represent that mathematically by writing M is proportional to Q. We said M is the mass of the substance deposited, and Q is coulomb of electricity that is passed through the substance, or that deposit the substance. And then we try to get what Q means, which means what do you call it? The current multiplied by the time taken for the current to pass through a substance. And we now plug in this value to get the equation. And then we try to know what N represents, which is the number of mole of electron that is used to deposit the substance. And based on that, we try to solve this problem, and then eventually we're able to do the calculation. And this is the end of the video regarding the first law, the first Faraday laws of electrolysis. In the next video, inshallah, we're going to talk about the second Faraday's laws of our Faraday's second law of electrolysis. Thank you so much.